Section 9-3, two means with independent samples. The main idea here is to compare two populations by looking at their means. The textbook actually goes over two parts, but we're really just going to cover one. A part where they discuss the two different populations where the standard deviations are known rarely happen in real life, and so we will not be covering that. So our main focus would be taking a look at independent samples where the standard deviations are unknown or not assumed to be equal. Okay? So first, let's define a couple of terms. We have the term independent. Two samples are independent if the sample values selected from one population are not related to the other population. Dependent. It says two samples are dependent if sample values are paired. So each pair of values consists of two measurements from the same subject. And so some examples of this would be like a before, after, a pre-post test or something like that. Each pair of sample values consists of matched pairs, such as husband or wife data or something, where one set of data is dependent on the other set of data. So just a quick example, some examples of independent samples. We have researchers investigated the reliability of test assessments on a group of 30 students who took proctored tests, and then there's a different group of 32 students who took an online test without a proctor. So two samples are independent because the subjects were not matched in any particular way. And here's an example of dependent samples. Students of the author collected data consisting of heights of husbands and the heights of their wives. So this is not the same person, but they're paired nonetheless by husband and wife. So there's 5 pairs listed below. The data is dependent because each husband is paired up with his wife. So this is the type of analysis that we will do in the next section. In this particular section, we will focus on independent samples. Okay, more particularly, we will focus on independent samples where the population standard deviations are unknown, or we're going to assume that they're not equal. Again, this is more likely the scenario, and the other scenario we will not cover in our presentation today. So, here are the requirements. We have the population standard deviations are unknown, and we are not going to assume that they're equal or anything like that. So we can be as free as we need to be. We have the samples are independent and simple and random, and then we also want them to satisfy the conditions where the two sample sizes are large enough, or both samples come from a population that are normally distributed. We have our notation again for the two different populations and samples, and we'll use a sub 1. So we have a population mean, population standard deviation, and the sample size, sample mean, sample standard deviation. All of them have a sub 1, and corresponding notations for the second population would have sub 2. So here's our formula for the hypothesis test. This is our test statistic. Again, mu1 and mu2 are assumed to be equal in our null hypothesis, and so mu1 minus mu2 will be assumed to be 0. We have the difference in the sample means minus the difference in the sample populations, which we're assuming to be 0. And then we're dividing it by our special standard deviation combination with the sample sizes. So we're using a test statistic that has a t distribution, and so for the t distribution we will be looking at table A3. We also have a degrees of freedom information that we need to address because we're using the t-distribution. And there are many ways to find, or actually there's a couple of ways to find the degrees of freedom, but in this particular book we'll use the smaller of the two sizes, either n1 minus 1, the first sample size minus 1, or n2 minus 1, the second sample size minus 1. Just to not have to deal with this business, we will be using our calculators, but we'll also see this this critical value method in use. Along the parallel to this hypothesis test, we'll also be looking at the confidence interval, and it's the same setup. We have the difference in the mean, the sample means, plus or minus the margin of error, and our margin of error is given by your critical t-value divided by, and this is the same expression that we saw in the denominator of the test statistic. Again, the degrees of freedom will be the smaller of the two values, either n1 minus 1 or n2 minus 1. A little caution here, before conducting a hypothesis test, we want to consider the context of the data and the source of the data and sampling methods, and we want to verify that the requirements are satisfied. Let's do an example. We have researchers conducted trials to investigate the effects of color on creativity. So here's the scenario. Subjects with a red background were asked to think of creative uses for a brick. Other subjects with a blue background were given the same task. And the responses are given by a panel of judges. And then the researchers want to test the claim that blue enhances performance on creative tasks. So they want us to test a claim using a 0.01 significance level. Just a quick requirement check. We got the values of the two populations and standard deviations are unknown or not assumed to be equal. We have the subjects are independent and they come from simple random samples, and our sample sizes are over 30. So let's take a look at the statistics. From the data, we have the sample size for those people who looked at the red background. There were 35 of them, and their creativity scores had an average of 3.39 and standard deviation of 0.97. The blue background, we had a mean of 3.97, standard deviation of 0.63, and there's 36 of them. So going through the 8 steps for our hypothesis test, we look at the claim. The claim says that blue enhances performance on creative tasks. So we want to write that in mathematical symbols. So let's go back to our list and establish our first population and our second population. So the creativity scores, the means for the creativity scores, we're assuming that the blue is going to be larger. So let's establish that our red background people are population 1, and then the population 2 would be the blue background people. So we would want, according to the claim, we're claiming that the blue background people will have a larger mean than the red background people. So the blue would be the second population. That should be greater than the first population, or if we look at it vice versa, the first population would be less than the second population. So back to our statement, we can express that our blue group, that's the second population, is larger than our red group, or our red group, that's the first population, is less than the blue group. So this is our claim. mu1 is less than mu2. And then if the original claim is false, then mu1 must be bigger than or equal to mu2, and this will contain a condition of equality. That means that mu1 less than mu2 will be our alternative hypothesis. So we'll see that reflected in step 3 when we assign those two statements. Notice that they use the equal sign for the null hypothesis. It doesn't matter what you use as long as it contains a condition of equality. So we can have a greater than or equal to, or just plain equal to as long as we know that our claim is a strictly less than sign, and that's the alternative hypothesis. Our significance level is 0.05, and we're testing two independent samples, so we will be using the t distribution. And the formula for the test statistic is given in our next slide. In step 6, we see that this is the distribution, or this is the test statistic formula that we'll use. And when we plug in those numbers, remember that mu1 minus mu2 is equal to 0. And when we plug in those numbers, we're going to get negative 2.979. Now, sticking with the critical value method, or the critical region method, we would need to go to table A3 with the degrees of freedom of 34. And then we see that at a 0.051 tail level, our test statistic, our critical value would be negative 2.441. So our critical value of negative 2.441 will set the boundary. Our test statistic is to the left of that, which means it's in the critical region, which means we will reject the null hypothesis. Now, without using that formula, and just by using our calculator, we're going to go to the two-stamp t-test. Now, in two-stamp t-test, we will input the mean, standard deviation, and sample size for both of our samples. And then down below, if you continue down, you see that we're going to select the less than symbol for our alternative hypothesis. And now the pooled is no, and it's always going to be no in our scenario, because this is assuming that we don't know any information about the standard deviation. So if we were assuming that the standard deviations were equal, then we can possibly pooled yes. But since part of our requirements is assuming that the standard deviations are not equal, or we don't know anything about them, we will always select no for our class. And so we do the calculations, and we get the same test statistic that they have, negative 2.979 rounded off. But more importantly, we also get to pull out our p-value, which is 0.0021. And with the p-value, we can simply compare that with our significance level to make our conclusion. And because the test statistic doesn't fall in the critical region, we said we're going to reject also the p-value method, because our p-value 0.0021 is less than our significance level 0.01. Then we also come to the same conclusion, which is to reject the null hypothesis. In step 8, we write our conclusion in non-technical terms, and here we can say that there's sufficient evidence to support the claim that the red background group has a lower mean creativity than the blue background group. Now, they kind of had it stated the other way, where they say the blue background group had ended up being more creative, so you can say that as well. Those two things are saying the same thing. Okay, let's shift gears now and take a look at the confidence interval. Using the data from the color creativity example, we want to construct a 98% confidence interval to estimate the difference between the mean creativity scores for those with a red and blue backgrounds. So we start with the margin of error formula. We have a 2.441 critical t-value, and then we got our sample standard deviations and sample sizes. And the margin of error is 0.475. We got our sample means, and so we put that into the formula where we add and subtract the margin of error, and we get values. The difference is going to be between 1.06 and 1.0, negative 1.06 and negative 1.0. Now, you can see that they're both negative, and we'll make a comment about that in the next slide, but I'll show you how to use the calculators. For the calculators, we're going to go to second function, and we're going to go to stat, and then go to test and then look for 2SAMP-T int. So 2 sample the t distribution, and we're looking for the interval. In our statistics, again, the first 6 inputs would be the mean, standard deviation, and sample sizes for both samples. We got our confidence level at 0.98. Again, we're going to say pooled no because we're not assuming anything about the standard deviations. And when we calculate, we're going to get the same results, negative 1.05 and negative 0.10. Well, they had 0.10, but we have 0.11 here, which is slightly more accurate than what they had. So what does that mean? That means that we are 98% confident that the limits of negative 1.05 and 1.11 actually do contain the difference between the two population means. And so the final comment is that the limits do not include 0, which suggests that there is a significant difference between the two means. Okay, that is the end of section 9-3.